All right, we're back. We are on page 5 of note 17 of Calc AB. We're talking about accumulation functions. We're talking about the second fundamental theorem. Basically, we're just doing a lot of calculus at this point because once you kind of like know a topic, it's all about integrating it into all the other stuff that you've done. So for example, here, we're going to evaluate limits, but to evaluate the limits, we're going to need, I'm guessing L'Hopital's rule, potentially. And also, I think we're probably going to need the second fundamental theorem, and I can see the accumulation function. So let's try to do this. Let's see what happens. So L'Hopital's is kind of a tricky thing to deal with in this, the notation is weird, right? L'Hopital's is not difficult. Getting it right notation-wise is a matter of discipline for me because I didn't learn it this way. I learned that you just sub in and like the integral from 4 to 4 on the left-hand one here. So if I go from this 4 to the 4 that I'm subbing in, I'll get 0. When I sub in 4 here, I'll get 16. 16 minus 16 is 0. I was taught you just write 0 over 0 and you move on with your life. That is no longer the case. Now what you're going to do is you're going to say, independent of each other, so the limit as x approaches 4 of 4 to x sine of pi t dt is equal to the limit as x approaches 4 of x squared minus 16, which equals 0. Okay, so both of them are 0. So it's 0 over 0, but we're not writing 0 over 0. We're writing it this way. Therefore, by L'Hopital's rule, which I always abbreviate, the limit as x approaches 4 of 4 to x sine of pi t dt of so much writing x squared minus 16 is equal to, now we actually use L'Hopital's rule. So to do that, this is where your second fundamental theorem is coming in. The derivative of the top is the derivative of an accumulation function. So it's going to be the integrand, which is this, with the upper bound subbed in. So it's going to be sine of pi x, and then times the derivative of the upper bound, which is just 1, which I always write just to be on the safe side. And then over the derivative of the bottom is 2x. So this is going to be, now we can just sub in, right? So we're going to get the sine, this is actually a really disappointing answer after all this work, but we get the sine of 4 pi over 8. 8 is not 0, so we got an answer. Unfortunately, well, not unfortunately, I think it's unfortunate because I did a lot of work to get it. The sine of 4 pi is the same as the sine of 2 pi, which is the same as the sine of 0, which is 0. So this limit actually is just 0 after all of that work. So I always find that a little disappointing, but it's not disappointing, I guess. I mean, I'm disappointed, so I guess it is, but that's the work you got to do. So now this one, there's two things. So I can definitely evaluate this integral without switching the bounds and changing the sign, but I can't use the second fundamental theorem on it without flipping the bounds and changing the sign. So what I'm going to actually do before I even do it is I just don't even like looking at it that way. I'm just going to change it right away to root pi of, whoops. So it's going to be the negative of the integral from pi to x squared of cosine of t dt. So I'm not actually doing anything yet. I'm just changing the way it looks because I don't like it. All right, now it looks better. All right, so if I plug in root pi, I get the integral from pi to pi, which is 0. Then I get the tangent of pi. And the tangent of pi is what? Oh, the tangent of pi is 0 because the tangent of 0 is 0. And then the period is pi. So that gives me 0. So I have 0 over 0. Am I allowed to write that? No, I'm not. So what I'm going to do is I will say the limit as x approaches root pi of negative integral from pi to not root x to x squared of cosine of t dt is equal to the limit as x approaches root pi of the tangent of x squared is equal to 0. Okay, so now I'm allowed to use L'Hopital's rule. Therefore, by L'Hopital's rule, I just always hope that I don't have to do it more than once. The limit, the original limit, the limit as x approaches root pi of negative from pi to x squared of cosine of t. So I'm just rewriting the original limit here. It's all about the notation. There's a lot of things that involve limits are much easier to do than they are to write down correctly. And it's really, so you got to really focus on the writing it down correctly part, because that's where you're going to end up losing the points if you're, can't afford to be lazy on these. All right, so here, derivative of the top. So it's an accumulation function. So the negative is just going to be there. All right, it's going to be the integrand, which is cosine of t, with the upper bound subbed in. So that's going to become cosine of x squared times the derivative of the upper bound, which is 2x in this case, over, all right, the derivative of tangent of something is secant squared of that thing. So secant squared of x squared times the derivative of that thing, so times 2x. That's nice because those cancel out. Actually, we got a lot going on here. So this is, let's simplify the limit as x approaches radical pi. So the two x's are going to cancel. So that was nice. 1 over secant of a thing is the cosine of that thing. So this is really actually overall just negative, I say just as if we didn't have to do a lot to get it, but it's actually this. So this is the negative of the cosine cubed of pi, because radical pi squared is just pi. Cosine of pi is -1. Cube it, you get -1 times the negative is +1. Wow. All right, you know what I'm going to do? I'm going to check these on the calculator, and then I will come back in another video and do the next problem. So I know we didn't do like a ton of problems in this video, but I think the next one might take me a little while, so I don't want to like blast through it. I'm going to try this like straight through, just see if I can type in the exact thing. Limit as x approaches 4, because the calculator understands L'Hopital's rule, which is very cool. You don't have to do anything special. You just type it in, see what you get back. Sine of pi times t dt over x squared minus 16, and we get 0. So we don't know why the calculator thinks it's 0. So like we do have to check our work and make sure our work is right, especially when 0 is your answer, because as soon as you get a factor of 0, it's like all your other work could have been wrong, and just because you're multiplying by 0, you're going to get 0. So you definitely want to check your work on those, but like it's reassuring that the calculator also got 0, because we think it is 0. Square root of pi, this one's weird. So it's the integral. I'm going to type in the original problem. So not going to change the bounds and switch the sign. I'm just going to go x squared to pi and then cosine of t dt over the tangent of x squared. So you need to be in radians. I don't think I mentioned that enough. You can tell on my calculator I'm in radians because it says it up here. So I'm just going to press enter, and I get 1, which is what we got. So again, 1 is another one of those answers where like there's a lot of things you could do wrong and still get 1. So you really have to check your work, but the calculator does confirm it for us, and that's pretty nice. So let me go back to the notes, and then I'm gonna wrap this video up, come back in the next one, and take a look at the next problem, which looks pretty interesting. We got a graph, we got a crazy accumulation function. It's got a lot of stuff on the outside. But anyway, these are the problems we did in this video. So I hope you found this helpful, and I will see you in the next one.